talk is going to be about the semi-active control devices for improving the seismic resilience of structures. For the next 1.5 hours or 1 hour 20 minutes, I'll talk about this, and we'll have some small question answer session if the organizers permit. So my talk is going to be structured in this way. I'll introduce a little bit about why we need seismic resilience and why we need smart structures for that. What are the smart materials that are available? A little background about it, and the one particular kind of materials, which is magnetorheological material, and devices based on that. How it can be applied to seismic control, and what are the future directions in that. Before I start my talk, I want to acknowledge whoever contributed for this. My team here in ASTAR laboratory, who has been the backbone in helping me perform all the work here in the laboratory, and some of the students that I have worked with in the past year. And I've also got some funding agency support for continuing this work in different fields. So I thank IGSTC also for that. So a little bit about our lab. I think every one of you should be aware where our lab is, Structural Engineering Research Center. We are located at Taramani, Chennai, and we basically do research about, basic and applied research in various topics related to structural engineering, and we also do some industrial research and consultancy. We cater to societal development and strategic sector. We have 10 laboratories with us, including one of the lab where I'm working, Advanced Seismic Testing and Research Lab. I think this is a brief about our institute, which I'm sure many of you will be aware. And this is our laboratory, the laboratory I work with, which is the Advanced Seismic Testing and Research Lab. We have sophisticated state-of-the-art testing systems, which is mainly consisting of shake tables, and then pseudodynamic testing system. I believe Dr. Mohit, who gave lecture to you yesterday, my colleague, would have given a brief about all these things. So I'm skipping most of this part. So most of the dynamic testing we do in our lab consists of full-scale testing also, and some of the unique structures need not be buildings, some of the unique structures which I'm sure Dr. Mohit touched upon. So let us dive into the topic, which is vibrations, specifically seismic vibrations. The picture tells a lot about what happens to structures when it is subjected to vibration. There are seismically excited structures due to which the structure collapses, and there is also classical examples of wind excited structures which causes wind vibrations, which causes some sort of disturbances to the structure. And there's also very, very interesting one case study, which is called the Millennium Footbridge in London. When it was opened, there was like lakhs of people walking onto that, and the vibrations from the people walking onto the structure caused actually the building or the bridge to vibrate. So this was not anticipated. This was never anticipated during design. So this is one of the very peculiar cases of what happens to buildings when it is subjected to vibration. So the vibration could be anything. It could be wind, it could be earthquake, it could be something bizarre like this human excited structures. But our main goal as a structural engineer is to ensure that whatever be the vibration source, we want the structure to remain safe. Nothing should happen to the structure. It has to withstand whatever is the excess vibration that it suffers, more than the anticipated one. That is the philosophy we expect for designing the structures for earthquake also. So what happens during earthquake? So one important distinction is there is going to be ground acceleration that is acting onto the structure. So the ground is moving, and because of that there is some forces acting onto the structure. Why? Of course, we go back to the basics, which is due to the Newton's second law. Building is nothing but a mass, and acceleration is subjected, the building is subjected to an acceleration, and of course it's going to result in some sort of a force. But it is not that simple. But these forces happen. What happens to structures? We know that they collapse. That is one of the primary cause for cause of concern for buildings. So we see collapsed buildings, roads, bridges, whatever be the structure, and it in turn kills people. So there is a famous saying among seismic engineers that it's not the earthquake that kill the people, it's actually the buildings that fall on the people, and then the buildings that are the one that kill people. So that is one of the primary effect of earthquake. But now we are not, as a structural engineer, we are not even looking only the primary effect. We expand our area of interest, and we see that what are the secondary effects and what could be the long-term effects that can cause devastation after an earthquake. So this also falls on us. And as I said already, there is an inertial force acting, and when there is a building at rest, then it is subjected to acceleration, which is a lateral force that is coming onto the structure. So for engineering representation, we take it as a lateral force acting onto the structure. This is a simplified example of a single frame when it is subjected to a ground motion, and how the force will be represented onto it when you are designing the structure. But why the structure moves? Again, we go back to the basics, and most of the reason that it fails or it moves is because of resonance. So all of us know what is resonance, and when resonance of the ground motion matches with the resonance of the building or some of the parts of the building, there is going to be amplified response, and because of that, the building is going to fail. So this is the basis behind it. So there is a very famous example of this Mexico City earthquake, which happened in 1985. I'm really sorry, just a second. Yeah, which happened in 1985. So there, what happened is most of the taller structures sustained the earthquake, and most of the shorter structure failed. This was a beautiful example of how resonance affects in case of seismic excitation. So the Mexico City earthquake was one of the earthquakes famous for being the low frequency earthquake, and because of that, most of the buildings around 20-story tall, which is having a natural period of around 2 seconds, failed. So other buildings which are of different height remain undamaged. So as I said, resonance plays a major role into it. So if you see typical examples of how tall a building is and how much will be the resonance for each of the buildings. So the tallest it gets, the most flexible it becomes. That is the idea behind it. So it's not just buildings anymore. We have to see about different kind of structures. As structural engineer, we have to deal different kind of structures against earthquake. Structures like suspension bridges, elevated water tanks, dams, each having different natural frequency, different time period, and they behave differently for the same earthquake or for different earthquakes. Now let us see how we are classifying earthquake for design consideration. So we know that we are taking design basis earthquakes, which is reasonably expected to occur in the lifespan of the structure. And then there is a maximum considered earthquake, which is the most severe earthquake. So what we expect is for the structure to behave in a ductile manner so that it doesn't experience a brittle collapse or a sudden collapse for whatever these earthquakes that can come. So that is how the performance that is expected for the structure. So for any normal residential structure, it has to at least have only minor level of damage. Without any damage, minor shaking it has to withstand. And then for moderate shaking, it should not have any structural damage. All should be repairable damage. And to resist a strong earthquake, it should not collapse. There can be some damages and then some non-structural damages, but it should not collapse. So this is the performance that we expect out of a building for different the different earthquakes that I was talking about. If you take the Indian scenario, we were from 2002 to 2016, we were dividing it into different zones, and then we were, talking about depending on which zone you are, you design the structure. But now we know more and more about earthquakes. We know more and more about, the prediction of earthquakes. So the proposed changes in the upcoming code is now increasing the zones. And we are even increasing the land area that is covered in the each zone also. So this is a major change that is going to come. So most of the structures which are already designed might not, cater to the criteria that we are revising right now. Let us see some of the most common used seismic analysis methods. Of course, there is a linear static, linear dynamic, non-linear static, non-linear dynamic. Most of the times we revolve around this linear dynamic, where you take the dynamic effect of the structure, but don't take the non-linearity of the structure into consideration that much while designing. But we are going to see about structural control techniques now, which primarily revolves around this last method, which is the non-linear dynamic method, which is mostly consisting of time history analysis, where you take the dynamic effect of the structure as well as the non-linearity of the structure and the devices that it gets added with into consideration. So this is the most sophisticated design method that we can enter into. But why do we need these sophisticated design methods? We are talking about structures with increased flexibility. You want the taller, most sleek structures. We want the most higher safety level onto the structure. And also we want to reduce the building utilization materials. We want to go towards sustainable materials, all these things. So we have an open question in front of us, which is, can we make a structure really earthquake proof? Whatever be the, whether it is DBE, MCE, can the structure, withstand that? Theoretically, if you have to make a structure earthquake proof, whatever I showed in the screen has to be there. Like, it has to be smart. It has to have different, different control techniques for different kind of earthquake vibration. So all these things should be there in a single structure to make it earthquake proof. It has to resist the fire. It has to, because of the post-earthquake scenario that I was talking about, all these things should be placed in a structure for it to call a earthquake-proof structure. That is why, in reality, it is very, very difficult or nearly impossible to build something earthquake-proof. But we can make it earthquake-resistant to some extent. So there is a major difference between that. And when we are also thinking about, unique structure, but it also has to be economical. And it's not just because we are talking about seismic, we cannot turn a blind eye towards other, forces which are coming onto the structure. So if you take, for example, blast, which is also a dynamic load, you see the difference of how the structural behavior is. I mean, how the loading behavior is for blast loading and earthquake time history. So these are two contra requirements that we are going to put onto the same structure. The same structure has to withstand both blast as well as earthquake. And then we are now looking into a specific performance level out of a structure. The performance, you can tell whether your structure has to have a life safety design or a collapse prevention design or immediate occupancy design, how stringent it has to be depending on the type of the structure. And we are moving into resilience-based design concept, where, it's not just about the structure anymore. It's about the whole community level, how it is performing, how it is bringing back after a, natural disaster like earthquake. So when we talk about resilience-based design in terms of seismic, a scenario, it includes all the things such as technical, organizational, economic, social aspects. What are the primary effects? What are the secondary effects? What are all the, how do we quantify it? What are all the measures that we are going to use to quantify for the resilience-based design? And then if we are talking about disaster resilience, what should be the period of interest? Like how much should be the recovery time allowed for the structure? All these things are coming into play. So whatever parameters that we talked about earlier gets modified for resilience performance level, if you're talking about. So from a 2D, it becomes a 3D. So we want functionality, we want recovery time, we have intensity measures for which it has to withstand. So we divide the performance level based on this. It has to be, starting from it has to be safe and operational to something like safe but repairable, safe but usable. These sort of multi-criteria come into picture when we are designing the structure against resilience. So if these sort of stringent requirements come into play, can we rely on traditional methods to satisfy all these needs? This is the question as a seismic engineer we have in front of us. So when I talk the traditional based design, which is basically a strength or ductility based design, Most of the time, they may be possible, but they are highly uneconomical when we have to do for these sort of stringent requirements. So that is when we go for something like a response control based method. So in response control based method, basically we are looking for 2 or 3 functionalities. One is you minimize the structural damage and you control the response, or you modify the interaction between, how the structure and ground is behaving during an earthquake, isolate it in some other way, you push the natural frequencies away using some method, and then you make it efficient. So all these things you can do either by adding a stiffness based device, adding a damping based device, or adding a flexibility to the structure by something like an isolation device. So all these are done by some secondary devices that gets added to the structure. So you can, if you see the spectral acceleration curve, you can push it towards left or push it towards right or push it down or up, depending on what is the requirement that is required for the performance level or even the resilience-based performance level. So a building structure is not anymore just the structure. The building structure will have a primary structure, which is primarily designed to take care of the gravity loads. And then there are seismic members additionally added to the structures to absorb the extra energy. So what happens during these earthquake? How do they divide themselves to take care of the energy dissipation? So in small and medium earthquakes, a conventional structure mostly remains elastic. But when the earthquake is large, you want it to be inelastic, and then you kind of push the based on the ductility of the structure. You make the structure safe. You dissipate the energy, allow some damage, and you make the structure safe. Whereas if you're talking about this damage control strategy, you want the structure to remain elastic no matter what earthquake comes. So the structure will be always elastic. The primary, in this slide, whatever the primary structure that I'm talking about will remain elastic. Whereas the inelasticity, the energy dissipation comes from the secondary device that you add to the structure. So depending on, if it's a small, medium structure, the secondary device has to dissipate the energy accordingly. If it is a large earthquake where you require more inelastic response, the secondary device can sometimes fail and dissipate the energy, but you can replace the secondary device and keep the primary structure safe because they are still in elastic range. So this is the design principle that we work around for the response control based method. So this comes majorly under a design method called a performance based design. For structural control, how we do that is you determine what should be the target grade of your structure. Like I said in the previous slide, what is the level of performance expected out of the structure? You determine what is the input earthquake ground motion based on the codal provisions, or if it is important structure, you can take site specific spectra, something like that, and then design the performance criteria corresponding to the target grade of the structure by adding a structural, by modifying the structural design by adding a structural control technique. And then you do the nonlinear time history analysis, earthquake response analysis, which is nonlinear time history analysis. Find out whether your response is conforming to the performance limit that you have set. If it is not, you go back and modify the structural control parameter that you have used and do this iteration until your structure meets the required performance. So this is the design method that we follow for structural control based technique. So how do we do that? Of course, we need to use something like a smart material. So the structure becomes a smart structure. So what happens is it senses any changes in the environment of the system. So it should have sensors. It should diagnose the problem at critical locations, and then it should store and process the measured data. So it should have something like a control computer. The performance is exceeding, the performance is within limit, something like that. If the performance is exceeding, it should give a control command action to bring the structure back to its intended performance. Say, for example, if you have to preserve the integrity, if you have to preserve the serviceability limit, like immediate occupancy, all these things. So it should, bring the structure back by some kind of, control action. So in civil engineering structure, so the smart structure technique has been in use for most of the automobile, aviation sector, automobile sector. All these regularly use this, control system, but they are successfully using it because the size is less, the actuation that is required, the force that is required is less. For civil engineering structure, it is usually the load that you're considering is also very extreme. There is extreme wind, there is strong earthquake, and also we want very high performance safety levels from the structure, especially structures like hospital power plants. And then we also give something like, all sort of unique structures. So everything is big, everything is unique for us. That is why a civil engineering structure, it is more challenging to adapt the smart principles for civil engineering structures. But the principle remains same. We have a structure. We will have sensors. These are the, what you're seeing in the screen. This is actually the components of a control system, typical components of a control system. You'll have a structure. You'll have, sensors that tells what happens to the structure. You'll have a controller, which is like a brain for the structure, and you'll have an actuator, which is the hardware part that does the command action. And based on the command action, if there is a seismic input, if it has to be, controlled, there will be a control input that will be coming from the controller, and the actuator will do it and bring the structure back. So this is the control system architecture. So how do we do that? We, use several methods. We classify the structural control technique majorly into 4 categories. There is active system, there's hybrid system, there's passive system, and semi-active system. I think many of you are aware how these systems are working, so I'll just briefly touch this upon and rush through it. So if in a passive control system, the major thing is the passive device does not require any energy to operate. So they are mainly made up of something like metals, which can yield and dissipate the energy. So if you see the architecture wise, you'll have the structure and you'll have the control actuator. You won't need a sensor, you won't need a control computer, because all these passive devices, once designed and added to the structure, they cannot be modified. So you don't need a sensor, you don't need a control action. It's just the plant structure and the control actuator that will be in play. Because of that, they are very, very energy efficient. They are very energy efficient, and they impart forces that depends on how the performance of the structure or how the performance of the secondary devices. And then they do not require energy source, which comes very, very handy during earthquake. So what is the principle that they use? Mostly, as I said, it is energy conversion. So it could be frictional devices. It could be yielding of metals. It could be phase transformation of metals. These are the principles that they use for dissipating the energy. So from one mode to another mode, they dissipate the energy either by deformation or by phase transformation, depending on the material which the device is made of. So some of the classical examples of passive devices, the first one is a passive damper, which is made up of metal, and then base isolation, which all of us know. And then something like a tuned mass damper, which is primarily used for wind applications. So this is the energy dissipation principle for passive devices. So the straight opposite to that is a more sophisticated system, which is the active control device. In active control device, you have everything. You have structure, you have sensors, you have the control computer, you have the actuator. So every action depends on how much it is needed and how fast it is needed. So all these things happen in a closed loop control system. So the advantages of it is very, very efficient. It works wonderfully because how much it is needed, you are going to give only that much level. But one of the major disadvantages of this active control system is they are very, very sophisticated instruments. They need equivalent energy to operate during earthquake, which sometimes proves to be challenging. So that is, however, there are some active devices. I think Mohit would have told about this yesterday. So let me not go into the details of it. Then we go into the semi-active control mode. So semi-active control, what it does is it takes the advantages of both active and passive system, and it forms a bridge in between. So here also you are going to use the device only when required, how much it is required, only like that, depending on the need of it. But the devices are made up of something like smart materials, which do not need high energy. So they work like a passive system where, you can actuate it just using a battery sometimes. So that comes handy during earthquake. But like an active control system, they work based on how much it is required. So they are response control based. So they are very, very efficient. So these are called adaptive devices. So these devices can be dampers. Most of the time, the dampers, these actuators are called dampers in common name. And one of the dampers that we are going to talk about today is the magnetorheological damper. So they are called controllable dampers. So how a controllable damper works, on the outlook, it looks exactly similar to that of an active system. But the only difference is whatever is the damper or whatever is the isolator that you're going to use will be adaptive in nature. So this is the difference between a passive and a semi-active control system. So if I tell that a smart material is needed for this, what are basically smart materials? So the smart materials is nothing but, they can change between two engineering fields, like, two phases we talk about. So for example, we can divide the engineering, phases into electrical, thermal, magnetic, and then mechanical action. So there are a lot of engineering fields we talk about. So if you take a material, if it operates in more than two engineering fields, then we can safely call it as a smart material. So the smart material are primarily used as actuators as well as sensors. So if you are using as an actuator, what it does is it takes from one physical field, which is like electrical, thermal, optical, magnetic field, and then the signal from that, it converts into a mechanical action. So if it does this, it is called a actuator. The reverse of it, that is, if there is a mechanical action, it senses it and gives a voltage signal or electrical signal out of it, depending on the mechanical action, then it is termed as a sensor. So a smart material is used both as actuators and sensors. Some of the commonly used smart material which everybody knows is the piezoelectric smart material. So the PZT can be used both as a sensor and as an actuator. So in a sensor, you will see that there is some mechanical action that is happening. Because of it, there is a voltage that is coming, and the sensors will tell us what is the relative voltage difference due to this mechanical action. If you see the inverse piezoelectric effect, due to the voltage or current that you pass through the piezoelectric sensor, there is a mechanical action that happens. That mechanical action can be used to control whenever we need, a reverse force or a force that brings back the structure to equilibrium. So these sort of control forces can be used from the actuation principle of PZT actuators. So let us see what magnetorheological devices does. Magnetorheological also is another smart device. So they are typically available in the form of MR fluids, MR elastomers, MR gels. So what happens in a MR fluid, for example, is there is a suspension medium which is fluidic in nature, usually something like an oil, on which there is something called magnetic particles, the carbonyl ion particles that will be suspended. So when there is an external field, one of the physical field that I'm talking about, which is the magnetic field in this case of MR damper or MR fluid, when there is a magnetic field acts onto this fluid, the ions inside reorient themselves and then affect the viscosity of the liquid in which it is dispersed on. So when a magnetic field is given, depending on the intensity of the magnetic field, these ion reorientation happens, and this changes the viscosity of the fluid, maybe from a semi-viscous to a little bit of solid, semi-solid state. And because of this, the yield strength of the fluid changes. Now, this is what happens in the material level. So when you use this material in a device, say, for example, a damper, this is what causes the change in the damping property in the device. So depending on the operating mode, there are various dampers, there are various devices that use this MR fluid. So there are three operational modes. Most of the operational mode which is used in dampers, they are, they form, what happens is when there is a magnetic field given, the yield stress of the liquid changes. That changes the viscosity of the fluid, and that changes the damping characteristics of these dampers or the shock absorbers. So how do an MR damper look? They look something similar to a shock absorber that you see in bikes. One biggest advantages of these MR dampers is they are very stable. They are very fast in responding to the external stimuli. So they are very, very, quick response devices, which comes handy during seismic control. But these smart devices, if they are very good, why can't we use straight away to the structure? So one of the biggest, challenge in using these devices is their highly nonlinear property. So what you see in the screen is actually the force displacement and force velocity characteristics of such dampers. So as you can see in the screen, whenever the current or the magnetic field varies, the force velocity, force displacement characteristics also varies along with it. And primarily, as you can see, they are bilinear. They have some region here, they have some region here, depending on where the velocity is. So they are not exactly linear. When the velocity increases, force also increases. That do not happen here. So what happens is, first step, if you have to use these devices to a structure, you need to characterize them. What do you mean by characterization? You need to find out what happens when you give certain frequency. You need to find out what happens when you give certain input parameters to the structure and find out what is the force that is getting developed because of it. So there are two kinds of dampers that are existing in market. So when we started this study, we didn't concentrate on developing damper. We wanted to see, like, if a market existing damper is there, how can we straight away use it for structural control. So we took two type of damper which was commercially available, and we subjected it to different kind of dynamic excitation. So our aim was to see like how the force response varies when the input parameters vary. So the energy dissipation capacity was the interest for us. So we started studying it by giving it different velocity, different current, and see how the dampers behave. So the only difference between both these dampers is the stroke length. Stroke length is different, but apart from that, the force capacity, everything almost remains same. So first, let us see one of the parameters, which is current, which changes the viscosity of the liquid. So of course, when the current changes, when the input current changes, you can see that the energy dissipation happens. And this input current change, when the current increases, the energy dissipation again increases non-linearly. It is not linear in nature. And depending on the stroke length of the damper, the stroke length of the displacement, input displacement, that also varies. So then the next thing was the frequency of operation. When we change the frequency and when we change the amplitude, we can see that the response is non-linearly varying. So this establishes that the most of the input parameter, which is the current or the magnetic field, amplitude of vibration and frequency of vibration. All these three are important in our dynamic excitation. So all these three are resulting in a nonlinear response from the damper. So now we know that it is a nonlinear response. The next step is, how do I characterize it? Meaning, if I have a combination of frequency, damping, and frequency, input excitation, and current, how much is the force that is getting generated? So this relationship should be established. So this is called a dynamic characterization of the device. So that was done. So how do we characterize it? There are, this is nothing but another spring mass damper device. You can use parametric modeling techniques. There are various models that are available for modeling these kind of dampers. One such model we took, and we tried to model it, and we tried to find out whether we can capture the force velocity and force displacement relationship. To some extent, it was capturing the force displacement, but not the force velocity. So we resorted to some other simpler models. We wanted to see how best we can capture the force velocity, because the velocity is one of the important parameters to determine whether we can use a damper or not. And that is going to come in handy to choose a damper for our application. So we chose some simpler models, something like a lumped parameter model, to capture the velocity profile of the damper. And we were able to do it and do it successfully. And there are also, at that time, we have a lot of data. Why do we have to go for intrinsic equation-based models? Why can't we go for non-parametric models? Because we have data. We have database models that are available. So we tried our hand on that also. So we tried to model the damper with ANSYS modeling, which is something like a black box model anybody can do. So if you have the force displacement, force velocity relationship, and we found that even the ANSYS model is better in capturing the force displacement as well as force velocity relationship to a greater extent. And one big advantage of this ANSYS model is inverse modeling, which we need when we have to use it for seismic. If you velocity acceleration, what is the force that is needed? The reverse of it can also be utilized. That is, if you need a force, I know the distance, what should be the current I have to give to achieve that force. So this is the inverse principle of it. That can also be done easily using these database models. And when we are modeling this, we found one very interesting thing. This is particularly for the research scholars. So we found that the liquid is yielding. Because of that, the energy is dissipating. So the energy has to get converted into one form, right? From one form to another form. And we found that it gets heated up when the fluid is shearing. When the damper is operating, we observed that there is a lot of heat that is generated by the damper. So we thought that if there is heat, of course, our liquid is responsive to heat. Does it affect the energy dissipation capacity? That was a doubt for us. So we introduced another parameter, which is the operating temperature. This is not the temperature. There are a lot of studies that were done on environmental temperature. That is, if you are using this damper, say for example in Chennai when it is 40 degree, when you use the same damper in minus temperatures, which is something like Ladakh, if you are using, can I use the same damper? So that is the operating temperature. That is the environmental temperature. But what I am talking about here is the operating temperature due to the operation of the damper itself. So when the damper starts operating for some n number of cycles, it dissipates energy and it dissipates as heat. Whether that heat affects the energy dissipation capacity. So that study also we carried out, and we found out that yes, between the first cycle and say for example 10 cycle or 11 cycle of operation, you find that the energy dissipation is actually reducing. It's more prominent when the current is increasing. That is, if you want more damping from the structure, if you give more current to the damper, it heats up the damper, and because of that more current, it actually reduces the energy dissipation capacity. So this was one of the important findings that we found, that it's not just the three parameters that control the damper. We also have to take care of the heat that is generated from the damper. So one parameter we wanted to make our model also adaptive for that. So we like a support vector regression model. This is another data-based model. I'll not go into the details of how it is modeled, what is SVR, all those things. So basically what we did is we introduced another input parameter, which is the temperature, along with the displacement, velocity, and current, which was already the input parameters that determine what is the force that is getting generated. So we took these four input parameters and we formed the input layer, and the nonlinear characteristics is modeled using the kernel layer, which gives what is the output of our output force for our damper. So there are various parameters for this, how the parameter is optimized with different optimization techniques. That is what I'm showing here. This is not much of a interest for practicing engineers, but for research scholars, like you can find out which model will be better suited for modeling your technique. And we found out that one of the meta heuristic models is actually better and computationally effective in calculating these force displacement and force velocity. So this is the first part of it. Like you have a damper, you need to find out what are the parameters that affect it, and then you need to find out how to model it so that you can figure out if I need a force, what should be the current that has to be given. So this, without figuring out this area, we cannot adapt the damper for our application. So this is the first part of the lecture where I'm talking about how if you are choosing one of the smart materials, how you are going to utilize it for structure. So the first step is characterization of the damper. Next step we are going to see is